Okay. Oh, that's very loud. We are back, right? So welcome to Introduction to Scientific Computing with Python. I want to remind you that today is the teaching survey at the end of the lecture. Please complete it. It's the only requirement there is to take part in the midterm. The midterm is next week. Okay? So if you miss today the chance to complete your teaching survey, please contact the TA. Last week we looked into numpy. We already saw how to create simple arrays, how to use the zeros function, the ones, the diarc, the from function, and we had first contact with lambda. So today we continue, and very soon we're going to look into plotting. So let's see, here are the attributes again that you should know, right? So size, shape, endim, and data type. You also need to know, let's check here. Wait a moment. Here. Right, so here in this table, for example, I give you attribute in the description, and you know that you can apply them to numpy. And array objects, we actually also looked into the different shapes, ranks an numpy array can have. We looked into the data types, so we have integer arrays, we had float arrays, we had complex arrays. Right. Different shapes, different dimensions, we reorder this. We had the discussion on what we define as difference between array and vector, or matrix and vector. We analyzed how we get this information, for example, through shape. We also used rank, and then we so here to get the rank we use endim. That would be a tensor, rank 3. We had an example about the Levi-Civita symbol, and there's a home assignment pending because I showed you how to implement that through hard coding in Python. But there are, of course, more clever ways with conditional statements and checking the index of an element of an array. Okay. We had also, let's see, comprehension questions. Very good. And now we can go into the difference that we discussed before. We here, for example, have a list and list comprehension on the bottom where we test the data type. And when we use this list to convert it to a numpy array, we see, hey, this is just numpy strings suddenly. That is not actually what we want in numpy very often, so we need to be very careful with our data types. Right. Different ways of creating arrays, zeros, ones, and diarc. We passed this. Very good. Something new, finally, after 6 minutes of talking. Calculations with vectors and matrix. So what vector matrix multiplication, matrix multiplication, and inner product of vectors and outer product of vectors. So that's what we do today. So there are, of course, some simple operations, right? Plus and minus. That for a vector, the matrix, you know very well and can be easily. Shall we try something? Yeah, so I claim something. We should always find an example. Let's see the slides. Not yet. So we just create a new notebook very quickly. Right, so if you don't know what I'm doing now, practice more because this basically should be known within your fingertips. First, we always import the module, numpy. And then we need a simple vector, for instance, 1, 2, right? So this vector we call vector A. So far, so good. Then we can say vector A equals vector B. So far, so good. Can you follow this notation? Right, so this multiple assignments at once in Python is one of the features. And then we could say vector A plus vector B is what? Yes. 1 time, 2 and 4. It's a very simple syntax. It's a syntax you could have guessed. So shall we try VA minus VB? That is 0, of course, because they are identical vectors. So we have the same direction with the same length. So far, so good. And now vector-vector multiplication. What do you expect when I tell you multiply vector A times vector B? So VA times VB, what do you know it is? Don't use Python, use your head. Vector A times vector B is what? Well, 1 times 1 plus 2 is how much? Is it 3? Is it 4? Is it 5? It's 5. It's 5. 1 plus 4 is 5. Yes, okay, good. So, but now let's check Python, what Python is doing. That doesn't check out, right? So we need to be a little bit careful there. And now please look very carefully. Can you divide two vectors? Vector A divide by vector 2? Have you ever done this? No, this is one of the different things cannot be done. Oh my God, what's Python doing here? Right, so you must clearly understand that your mathematical operations are not exactly what the symbols now mean in Python. If we want to restore the vector-vector multiplication rules, we need to use special methods, special functions. Your arithmetic symbols, they work, however, now element-wise. So if I just look at a number, at a vector, right, with another vector number, right, it actually makes sense. So 1 plus 1 is 2. We have that. We are here. 1 times 1 is 1. 2 times 2 is 4, right? 1 divided by 1 is 1. 2 divided by 2 is 1. So in Python, when we have vectors, or actually numpy objects that we think are vectors, our arithmetic operations function element-wise. So they don't take the whole thing as a vector, they take it number by number. And that is because they are actually arrays and not vectors. So far, so good. We take them as vectors and matrices, but internally they are still arrays. So today we try to figure out how to restore our normal vector, or restore our linear algebra. So let's see what we have to do. We have to look into the element-wise operation, plus, minus, multiply, divide. This is what we actually did already, right? Very easy. And then add, subtract, multiply, divide, power. Yes, we can do this. Remainder we can do. Reciprocal value. But with reciprocal value, we must be very, very careful. What's the reciprocal value of a vector, of a matrix? We call it normally the inverse. Okay. And inverse, there are special rules again. So let me just see. So VA modulo 5. So there I get some values. Do the values make sense? Well, in VA we had 1 and 2. And when you divide by a number that is bigger than the values, I always get the number of the remainder operation. Okay, make it more interesting. How about 2? Then I should get 1. What should I get? 1 and 0, right? There we go. Because 1 divided by 2, remainder is 1, and 2 divided by 2 is 1, remainder 0. So far, so good. Let's play around a little bit more. VA remainder VB. We are at element-wise operations. So here we get 0 because VA equals VB. Okay, so what else? VA to the power of VB, does it work? It also works, okay? Again, these are element-wise operations. We have here now 1 to the power of 1 and 2 to the power of 2. Yes, very good. Today, many people of you not. That's very good because then I get a little bit of feedback if you still follow, right? If I'm too fast. Okay, very good. I appreciate that. So let's see. So here we have some more examples. We can go through more slowly. Now, we already have seen we can use the plus symbol for the arithmetic operation addition. Now I introduced you some syntax. Right? I introduced you the addition as a numpy function. This has two purposes. First of all, I introduced the method. And second of all, it's our alternative to use array or vector operations using numpy pre-built functions. So let's see how this goes. What's going on here? No, make big again. Very good. Shift a little bit. Here we go. So numpy.add. First of all, I like to check what the function is. So I always do the help method or the magic symbol, right? And it tells me here, add arguments element-wise. So far, so good. So this is nothing really new to us. So we expect now to get the same result as our VA plus VB. Yes, it works. Fine. Let's go back to the slides. Okay, so what else do we have? So here now in this example, right, we actually have two areas 2 by 2 or matrix 2 by 2, right? We have print M1, so these are 1, 2, 4, 5. Print M2, this is -1, 2, 5, -4, and in this line below I add them up. So I get 1 plus -1, and that is 0, and then on the diagonal 5 plus -4, that is 1. Oh, maybe correct, right? I checked half the results, seems to work. Important, when I now add the new function, add, right, numpy add M1 and 2, I get the same result. Good. That's already all. Now we can do the same thing with subtract. Right? The function definition is sort of similar. So here you have the simplified syntax, numpy subtract, array1, array2. Then again, I have here an example where I take the 2 with my arithmetic symbol minus and 1 with the numpy method, and I get the same result again. So now we know how add and subtract works. Multiplication. So this is where the differences start. Right? So when we multiply two vectors to matrices, we get an element-wise operation without multiplication symbol. When I give you a task like this, two matrices separated by a dot, that means inner product. Okay, this is kind of important to me. Inner product, not outer product. If you don't know what's an outer product yet, you will see it in this course very soon. But the inner product you should simply know is matrix multiplication, vector matrix multiplication, or vector multiplication. Right? I just call it inner product. Okay. So what do you get here? How do you do? What do you get? Anybody want to tell me? Yes, you can just go to the next slide and you see the result, right? Okay, but if you don't know, right, try to remember, because what we do here is basically high school math. And how do you know that Python is not lying to you, or that you didn't do just a silly mistake? You need to know what to expect. Then you check that everything is functioning properly, and then you use it, right? So these are three steps. You always need to validate that everything is working. Like when you ride your scooter in the morning, you don't just jump on your scooter. You switch on the engine and then you go off. You check that all the lights are functioning, that the brake light is functioning, that your signals are functioning, and that you have enough fuel in your fuel tank, right? Ideally, you also have a look at your tires, and then you start riding your scooter for safety. And if you don't, then you should do this. It's very important that you are safe. Okay, so anyhow, so I think I know how this goes, right? So I take this number here, 1, I multiply with -1, and then I add 2 multiplied with 5, and I write this in the top left. And then I go to the 1 times 2 plus 2 times -4, and I write this in the top right. So I have the first row, and I do the same for the second row with 4 times -1 plus 5 times 5. And then what is that? 4 times 2 times plus 5 times -4. Yes. And then I need to do the multiplications and summations and subtractions. And then I should get something like 9, -6, 21, and -12. And here's the thing. I like to use actually Python to check if what I do in my head is correct. So after I wrote this down, I went to Python, I did the multiplication, and I checked that this is really true. And so when you look at this now, right, this is very, very different. But remember, this multiply is element-wise. So here you see the comment in line 3, element-wise. That's not what we want. We want to have this time a proper matrix multiplication. And here again, explained very nicely. I think I took this from some book, maybe even the course book, right? Because it's a very nice figure. I need to go away. So what do we do, right? There are a few works around. There is the work around I recommend you to do. That is using the dot method. Dot for dot product or product, right? So then you have two matrices, M1 and 2, or A and B, and you pass them as arguments, and you get the correct result. Then something more specialized is matrix multiplication. Again, takes two arguments, matrix 1 and matrix 2. And the alternative that works since I think a few years is actually the at symbol. That means proper matrix multiplication. There's one more way to do it. And this is actually defining some matrix objects directly and using multiplication. So anyhow, let's check this out, right? So we always try to validate whatever we do here. Where's my, here it is. Okay, so we have numpy dot. First thing you do is what? No idea, right? But what is first thing I do? Question mark, right? I check what it does. Dot product of two arrays. Very good. That's exactly what I want. Okay. So what do? V1, VB, V1, VA, VB, and we get 5. So far, so good? Okay. So next example, numpy. Do you remember next example? What was it? Matmul, right? First thing I do is exactly check what it is. Matrix product of two arrays. But now the question is, I have vectors, right? I don't have matrices. So will it still work? That is the question. I do not can fix it. No worries, still works. Very good. And last one, VA, VB, not comma, but the at symbol, right? Like in your email. Blah, 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 at Google, blah, 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 and whatever, right? Okay, good. Yes, it also works. So far, so good. Mhm. There's one more way I can show you, and that is using a matrix object. So clearly distinguished, right? In numpy so far, we have used arrays. We, humans, right, think of the arrays as vectors and matrices or tensors. But for numpy, they are just arrays, just numbers in some memory. If we want to tell a numpy, no, right? We actually do have a matrix. Then we use the matrix method. So I can just here define my matrix for 5. I call this M1, okay? And I call this M2 as well. So far, so good. And now I do M1 times M2. The question, is this now element-wise or is this a proper matrix multiplication? Numpy dot M1 comma M2. That's how I can check here, right? And it's actually the very, very same result. So I showed you 4 ways of doing proper matrix multiplication, and actually also with vectors, so proper inner products. Okay. Try to remember 1 or 2. Ideally all, right? But we're all just human. So 1 or 2 would be perfect. And remember what it's supposed to do inner product. Remember what it is not supposed to be, right? The element-wise product. And then it should be all right. Comments, questions so far? You're just sitting there, but this is a big moment in your life, doing proper matrix multiplications in a computer, because that's what scientists do all the time. The next big moment will be how we do a diagonalization and how we form an inverse of a matrix. Let's see. Yeah, because actually you can do so much with these simple operations already. Where you have to go? I have to go here, right? Okay. So this is again a very important. We will have a detailed look in section 253 matrix and vector operations. Okay. So this was just the start. There will be more. Okay. So now division. Division again is not defined between vectors. It's not defined between two matrices. It's not defined between vector matrix or matrix vector. So don't do this. We normally multiply with the inverse of an object, but then have you seen an inverse of a vector? No. But you've seen the inverse of a square matrix, right? There's actually also have you seen the inverse of an n times m matrix? Let's suppose you don't have a square matrix, 2 by 2, 3 by 3. Have you seen the inverse of 2 by 3 matrix? Or 3 by 2? No? Also can be done, but then it's called a pseudo inverse. Just in when you encounter it, it's a pseudo-inverse, because there's a trick to do it actually. Okay, so remainder operation we saw. Here is the example using a numpy function. First one is the matrix or array. The next one is the value we want to find the remainder for. And one remainder 2, easy. Here's a good example, I think. Numpy range to 7, so we get 0, 1, 2, 3, 4, 5, 6. Right, and then we do a remainder. Of course, right, 0 divided by 5, we have 0 remainder, and then 5 divided by 5, we have 0 remainder. But until then, we have an increasing number of elements with increasing value. Yeah. So 1, 2, 3, 4, 5, because, right, so this is, what is it? 0, 1, 2, 3, 4. 4 divided by 5 is remainder 4. And then 7 divided by 5. No, 6. There should be 6 here, right? So 0, 1, 2, 3, 4, 5, 6. 6 divided by 5, get 1 time and 1 remainder. Why is this not 7? Where's my 7? I asked for numpy in range 7. That's one of these silly midterm questions. Could be, right? That bring you or lose you quite a bit of points. Well, this one goes from 0 to 1 minus this one, right? If you want to get 7, you need to 7 plus 1. Because you asked for 7 elements and Python starts counting at 0. So this is 1, 2, 3, 4, 5, 6, 7th element, but 0, 1, 2, 3, 4, 5, 6 value. Good. Okay, reciprocal value. So this is important, but very, very careful. Reciprocal value is not the same as the inverse because this is defined element-wise. How do you know if a matrix is the inverse of a matrix or is just the reciprocal values? Well, when you take a matrix times its inverse, you should get a diagonal matrix with ones only, right? Okay, let's see. What can we do? What can we do? We go over here. So what we have numpy dot reciprocal, right? Numpy dot reciprocal. Yes, this one, and then M1 is what? 1, 0. How about S type float? Yeah, there we go. Did you see this? This is one of the. So remember, NumPy tries to give you a data type when you give a matrix, right? Here, the data type of M1 is integer. But the values of M1, 1, 2, 4, 5, okay, all integers, and the reciprocal will be what? 1? 1 and 1 only, but the reciprocal value of 5 is not 0, right? But we said it's element-wise. And the thing is, it will calculate 1 divided by 5, which is how much? 0.2, right? But then NumPy tells you, hey, this is 0. Now that doesn't check out because it will take 0 and will look at the data type. It's an integer matrix, so keep it as an integer matrix, right? But then 0.2 as integer, well, Python actually just cuts off some values, so that will be just 0. And you see this for all the other values as well. Good, how do we fix it? We as type. Right, so we convert our matrix from an integer matrix data type to a float data type. And then we see, yes, there are values. Very good. Okay, so now we didn't let Python trick us with the data types. But do you remember our actual question? Our actual question basically was, to show that this is not the inverse of a matrix. So when I multiply this now from the left or the right with M1, if it's the inverse, right, I would get the diagonal with ones, but it's not. And I see this, right? So it's not the inverse. The reciprocal is not the inverse of a matrix. Do you know how to say that in Chinese? It's not the inverse? Inverse, it's not the inverse of a matrix.
I'm not sure.
You're not sure? Who knows the inverse of a matrix in Chinese? So that's the inverse of a matrix, right? But it's not that. Fan chu che. Very good Chinese, I know. Thank you. Okay, continue. Right, again, right? So not the inverse, please don't mix it up. Okay, so let's see. Okay. Even on the slide, not to be confused with the inverse. Why do I emphasize this so much? Because I've seen this too much wrong in too many cases, not only in the course but also elsewhere. So be careful. Right, and here's the example. Data type as float. Yeah. Well, look, here's a different way of using this. So we can use d type in the reciprocal method itself to specify what kind of data type we want. So we can go back, play around a little bit. So numpy, no, that's not what I want. Numpy dot reciprocal, and then m1 comma. Let's go comma d type. Now we have seen float many times today already. Let's try complex. Yes, okay, there we go. And complex, we actually can use, can take the real part, and then we get the same result. So far, so good. So if you forget this, right, as type, you always can use d type in most function calls in NumPy to make sure that you have the right data type. If you ask for complex numbers, you get the real part, and J indicates the imaginary part. But if you're like, hey, all my J's are 0, then you can just look for the real part by putting here the attribute real. And there we go. And this is the same as above if you remove the matrix multiplication. So again, there are many ways to get to the correct results, right? You just need to find one. So far, so good? Yeah. There we go. So we have other functions as well. So we have trigonometric functions that you would see in science and engineering quite a lot. We have the square root, we have exponential function, and the log function. Let's see, brief looks. So these functions also work element-wise. So I think there's one home assignment now, home assignment 3, where I asked you to like convert the degree value and radian value, because numpy actually works in, what was it? Not degree, but radian values. So you take like 90 degrees divided by 180 times pi, and you get the right value for, well, 90 degrees of sine is what? Do you remember? There's some special values you should remember. So sine starts at 0 and then goes up to 1, goes down to 0, and then minus 1, and then 0 again, right? And this whole thing is like 2 pi. 1 pi is half of this, and then so whole thing is 360, so it should be around a 0. Let's always choose the wrong window here. Let me see. So far, so good. NumPy. Actually, I don't want to have the matrix. I just want to check if this is really working. So I put 90 degrees here, and then I get 1, right? I put 0. Sorry. I put 0. I get 0. Okay, so there's my sine function. No, not this. What else? Square root also works element-wise. What's the good test for square root? Let's see. We can have numpy square root 2, right? That's 1.4 something something. How about numpy square root minus 1? What do we get? Okay, it doesn't work, right? So actually, we need to expand our hmm, our number. So from integer, we go to complex numbers or complex integers, right? And then square root is working because it recognizes, hey, now we are working with complex numbers. So the guy asking me what is the square root of minus 1 actually is okay with complex numbers. Right? So Python gives this. If you don't, Python just tells you, okay, fine, I don't know. Right? So that was written here. Invalid value encountered. Because you're not giving complex values. Complex value, you add 0j, right? So you, sorry, plus 0j. There we go. So far, so good. Bless you. Okay, let me see. Okay, so square root is also defined here. We can give d-type. Do you spot this here? D-type. So if you forget how this works with the trick with adding the complex space as an argument, we can just say -1. What was it called again? And d-type, right? D-type equals what? Well, we expect a complex number, so we write complex. Okay, also works, right? So far, so good. So far, so good. Okay, so exponential function and the log function we should maybe put together. So we have, how many log functions are there? I have here 2 log 10, then there's just log, computes logarithm of basis 2, computes logarithm of basis 10. Who of you is an expert for logarithmic functions? Who of you does not like logarithmic functions? No? You seem very indifferent, but it's okay. We can explore this a little bit. So let's take some number, right? NA. NA should be 2 to the power of 10. 2 to the power of 10 is what? Is one of the numbers very important in the computer, right? So this is like 1024. Is that right? Okay. So numpy log, so the logarithm, right, should bring me back, what was it? The value here or the value here? What was it? One is the basis, the other one is the exponent, right? And in principle, it should bring back the exponent. So when I ask numpy, hey, numpy log 2, what is the exponent of 1024? Either through NA or I can put in the number directly. It tells me it's 10. Because 2 to the power of 10 equals my argument, 1024. But very, very careful. NumPy, what? I don't want this. Very good. There we go again. NumPy.log 1024 is how much? Is it 10? No, it's not 10. Very good. It's this number. No idea, right? But it's this number. How about numpy.log 1024? It's also, well, I did this twice. Actually, numpy log 10 I wanted to do here. It's a numpy log is this number. So, do we understand what's going on? Well, a little bit, right? Because 10 to the power of 3 is 1,000. So far, so good. And 10 to the power of, well, whatever this number here is, all right? Copy paste. There will be maybe small rounding errors, but that's okay. Right? So tiny, tiny rounding errors, but it's 1024. If I don't want the rounding error, I say numpy round. So far, so good. If I want a few more digits, I say digits. Normally 8 is a good digits for intermediate results. No, not digits. Numpy around, let's check. Decimals, right. Okay, decimals equal 8. Okay, there we go. Up to this number. So now, this number here, numpy log, is which basis? We have 2 as basis, we have 10 as basis. What's left? High school math. What other important basis is there? Right, a to the power of b. B is the exponent, a is the basis. What other basis do we have that is really, really important? You do this a lot in financial math, right? When you go to a bank and they try to sell you some contract or you stay for credit, then they calculate something like propagation of interest rate. What do they do? Oh yeah, I'm pretty sure you know. So what is numpy e? Actually, it's capital E. No, it's small e. 2.71, the Euler number, right? And 2 points, blah, blah, blah. 2.71828 to the power of 6.9314 is almost 1024, right? So far, so good. So you have 3 different logarithmic functions seen today. I think there are more. There should be a log 8 function as well. Log 8 is also important for different reasons. See, is there? Not found, right? And 16, also not found. Oh yeah, maybe more specialized libraries have that. Okay, so we know how this works. Oh, there are some special functions. Real, imaginary, conjugate. We will look at this sine, absolute, floor, ceiling, and okay, round. Okay, so I think by now you should already expect that real and imag, right, give you the real and the imaginary part of a complex number. What does conjugate do? Let's see. So we had a matrix, right? M1. Let's call M3 equal M1 plus M2 times J. Okay. So my M3 is like a complex matrix. So times 1J. So now I have complex valued matrix. So far, so good. So numpy real will do what? Well, it should give me the real part of the matrix. Actually, maybe not that good here. Maybe times 3J. Okay. because we want to see the difference between real and imaginary right now, right? So numpy imag give me the imaginary part of this matrix, so 3, 6, 12, and 15. So far, so good. Now numpy dot conjugate does what? Well, if you don't know, you take the question mark and it tells you here conjugate. Do you remember what's a conjugate of a number? So if a complex number, right, you have a real valued axis and an imaginary axis. And you have a vector, right, somewhere on the plane, and the conjugate is basically you turn it around the real axis. So a positive complex argument becomes negative. So let's see. So conjugate of M3 is what? Yes. So we have 1, minus 3, 2, minus 6, 4, minus 12, and 5, minus 15. And now the funny thing is actually, if you, there are some uses why we have this. And one of this, you can define your own real and own imag function. If you subtract now the value of M3, you're only left with the complex values. And if you divide this by 0.5, multiply this by 0.5 divided by 2, you're left with the imaginary part. But you can do the same trick with the real part as well. Okay, what else? Well, it's a real example, but it's a toy case anyhow. Sine and absolute, that is fun. So M3 is what? So we see here they are all positive values, right? So numpy.sine just tells you, not saying sine, tells you, hey, is your value real? Real. Plus or minus? And it tells you, yes, it's plus, positive. It's different from the absolute in a way that numpy.sine minus 5 will tell you what? Will tell you minus 1 because it's negative. What will tell you minus 99? Minus 1 because it's still negative. So whatever you have a negative value, it's minus 1. So let's see, 0.008, still negative. Right? Doesn't matter how big. It just to tell you, hey, this is negative and this is not negative. So far, so good. So absolute works different. Absolute doesn't care about the sign, just gives you the value. Right? Plus, minus, and that is a good time for break actually. And after the break, we do floor and ceiling. Yeah.